Hello, space fans. Today we're going to be talking about maneuverability in space. And just like fighter aircraft are only as good as their maneuverability and acrobatic capabilities, similarly in space, it's becoming more and more important to be able to move out of harm's way when it comes your way and be able to position yourself in an advantageous position relative to your enemy. So, with that, we want to investigate what options are there available to us for maneuvering. And at the crux of all of this is one key concept, which is the higher your altitude, the slower you orbit relative to other people at a lower altitude, and the lower your orbit relative to people that are above you, you will be traveling faster. Okay, that is the heart of everything. If you understand that, then everything else will just bolt into place. So, with that, we're going to consider GEO to start with. The same principles apply at Leo, but at GEO, there's a couple of nice rules of thumb. So, we're going to start there. So, here I've just added Lucha Limp just to act as our baseline satellite that we're going to be performing maneuvers off. So, first things first, let's set the RI reference frame. So, positive radial away from the Earth, in track to our left. So, our velocity vector is pointing directly to the left. Left is to the east in longitude, right is to the west. Now, on your keyboard, you can press A and D on the keyboard to rotate around the geobelt. This is kind of a nice feature for being able to recenter the camera when you need to. So here I want to start with a particular maneuver called an in-track burn. And there's a nice rule of thumb where if you burn 2.84 meters per second in the in-track direction, so you increase your velocity by 2.84 meters per second, you'll induce a 1 degree westward drift at GEO. So let's just see that in action, and then I'll explain what's going on. So to do that, add a maneuver. So right-click, Actions, Add Maneuvers, brings up this window. Add a new maneuver sequence, and then let's add our first maneuver to that sequence. So a 2.84 meter per second in-track burn, and I want to perform it at the current sim time. And here we are. So let's just propagate this out and we'll see what happens. Okay, so there's the maneuvered satellite. Here's our original satellite. And you can see we create this 1 degree westward drift. So 19.07, and our original longitude was 18.07. Okay, so you can see every day we're going to drift 1 degree west. Now, why is that? So what we've done with this one in-track burn is we've raised our altitude on the opposite side of our orbit from our current position. We've kept our current position. We'll always intersect our current position. All we've done is raise the altitude on the other side 180 degrees from our current position. So we've created this eccentric orbit with an apogee that's a bit higher than it previously was. So that is what you're seeing play out here. When that maneuver happens, let me see if I can quickly jump back to it. Propagate back. Actually, it might be easier just to jump in half orbit blocks here. There we go. So what we've done is we've performed our in-track burn, increased our velocity, raised our apogee on the other side of our orbit. So our apogee is actually up around here somewhere. So we propagate it out. We should be able to propagate out to the next nodal crossing. So our apogee is around here. So that's where we've reached our highest point. We're still going to fall back down to our perigee, which will re-intersect GEO. And that's what you see here. We fall back down and we re-intersect GEO. So in practice, this isn't a very nice way to get around GEO because you're always re-intersecting GEO 1 degree to your west every day. So people who are to your west aren't really happy with you when you just keep dropping in on their position. So another maneuver that you can do here is adding another 2.84 meter per second burn at your apogee will raise your orbit altitude on the other side of your orbit by the same amount. So that will recircularize your orbit. So now we're in a circular orbit, but we're at a higher altitude. So we're traveling slower relative to everyone else per day. And here you can see we're drifting at 2 degrees west per day. So we've entered this nice linear drift where we're out of the way of everyone at GEO, and we can just cleanly move around the belt at 2 degrees per day. And it took 2.84 meter per second burns to do that. Maybe we didn't want to create a linear drift. Maybe we just wanted to perch ourselves 1 degree away, right? We just wanted to move 1 degree down to the belt and stop. We can do that too. I'm just going to propagate back here to the start. And we're going to remove this second maneuver. And this time we want to propagate 1 full orbit period to when we reach the GEO belt again. Okay, and now we're in this eccentric orbit. What do we want to do? We want to lower our apogee on the other side of the orbit back down to recircularize. All right, so let's do that. Let's add a negative 2.84 meter per second burn. Okay, and now we've effectively just shifted our orbit by 1 degree west. Okay, so that's 3 different scenarios there. One, just a dirty longitude 1 degree drift, costs us 2.84 meters per second. Maneuver type 2, we created a linear drift at 2 degrees per day by performing 2.84 meters per second burns. And then 3, we perched ourselves 1 degree away by performing our first 2.84 meter per second burn, and then waited 1 full orbit period, and then performed a negative 2.84 meter per second burn. Okay, so that's burning in track. Now, what happens if we burn in the other axis, so radially? So remember, positive radial is away from the Earth, negative radial is towards the Earth. Let's consider that. So I'll delete these maneuvers, propagate back just to the current time. Now let's consider the same thing, a 2.84 meter per second, but this time radial burn. And when you burn radially, you end up creating an NMC, a natural motion circumnavigation, at some point to your west in this case, because we burn positive radial, but you enter into a circumnavigation around a point to your west. So as you can see here, 2.84 meters per second, the same delta V as the in-track, it created an NMC which was about 0.1 degrees to the west. So I re-intersect the belt around 0.25 degrees to my west. Okay? So, and if we just propagate this out, you can see it performs this NMC, right? So we're now in this NMC 0.1 degrees to the west. We'll just continue on this track. So it takes a lot more delta V to burn radially to move 1 degree west. So 1 degree is all the way out here at 19. We're currently at 18, so 19 is all the way over here, right? So you can see we need about almost probably 8 times the amount of delta V. But let's try that. So I'll just multiply it by 10. Let's do 28.4 meters per second. Okay, so that roughly creates our NMC centered about 1 degree to our west, 19 degrees-ish. So if we divide that by 2, let's do 14.2. You see 19.1 degrees is where we'll intersect the belt. So it takes us a lot more delta V, almost 10 times the amount of delta V, to maneuver radially to get that 1 degree distance offset at GEO. And now you can see what it's done is created an NMC, so we're actually going to return to our original position if you wait a full orbit period. So every orbit period, you're going to return to your same position. But half an orbit period, you're going to have moved the whole distance that you wanted to have moved. So radial gets us there quicker because you're not initially traveling. When we burned in-track, you might have seen we initially went in the in-track direction before we curved back on ourselves and started going the other way. Radially, that doesn't happen like that. We just start instantly, we go up, and then in the direction, start traveling in the direction that we wanted to go. So here, We can do the same thing. If we propagate half an orbit period, you can see we've now intersected the belt. Just going to propagate back a little bit there. Now, to cancel this out and perch ourselves here at this 1 degree offset, we waited half a period instead of a full orbit period with the in-track burn. And instead of burning negative in-track, we have to apply the same radial burn. So in this case, 12.4 meters per second. Okay, and that will create our perch over here. I was wondering why I was a little bit offset. So let's go back in and change that. 14.2. Update. That's better. So now we've created our same orbit, but 1 degree to the west using only radial burns. But you can see here it's 28.4 meters per second instead of 2.84 meters per second. So 10 times the delta V. And we're actually left with a slightly larger NMC here. So that's burning radially. Now we can actually combine in-track and radial burns to maneuver even faster for even more delta V. It kind of only applies really at LEO, so we're not really too concerned with that. But you can see here, just from looking at this, burning radially is the fastest way to move your position. So if you're a fighter jet, it's kind of like the brake right, pull back on the stick. That's your radial burn to get you out of the way. It's expensive, costs you a lot of fuel, but it'll get you there a lot quicker. The kind of autopilot preferred fuel efficient route is the in-track burn in order to create either a dirty 1 degree westward drift or to create that linear drift that I showed you earlier. Now, the nice thing about this is it all applies in reverse if you just reverse the delta V's. So I'll show that to you next, and then we'll overlay both these maneuver types onto the same satellite so you can see them compared to one another. Okay, so here I've created the radial and in-track burns, and I've done it in both the prograde direction, so positive direction, and the retrograde direction, negative direction. Shown in green is the in-track burns. So we zoom in, in blue is the in-track burns, and in green is the radial burns. So this is the positive in-track burn, that's the prograde, and this is the retrograde in-track burn. This is the positive radial burn, and that's the negative radial burn. So the kind of neat thing, when you burn just radially, you can see all your delta V goes to increasing your altitude. So that's the first thing you can see. Your apogee's much higher. When you burn in the in-track direction, you can see you do increase your velocity and you start moving in that direction, but that just sends you to a higher orbit and whips you around here. So let's now propagate half an orbit period into the future and see where everything ends up. Okay, so you can see our 2 radial burns after half an orbit period have both re-intersected the GEO belt, and our 2 in-track burns have just reached apogee. Let's propagate another half orbit period. The 2 radial burns have returned to their current point. The in-track burns, they're gone because they're on an eccentric orbit now, so they are going to continue in their drift. So that's a nice way to summarize everything. I hope this all made sense to you. I know it takes a bit to get your head around all this. But yeah, with these kind of intuitive rules of thumb, 2.84 meter per second in-track burn will create a 1 degree westward drift. That's a good place to start. And from there, there's a bunch of other rules of thumb that we can create for radial burns. We can combine radial and in-track burns and things. But we're just starting out. So hopefully this has been insightful and useful. And you can use it for developing scenarios of your own. Thanks for your time. Happy hunting.